Okay, so in this video, I want to compare the two different approaches to doing conservation of energy whenever rotation is involved. I mentioned back whenever we were doing the parallel axis theorem that there were some things that weren't so obvious about how exactly you deal with translational kinetic energy and rotational kinetic energy at the same time. It would appear that it's as simple as, well, if the center of mass is in motion, then I should have translational kinetic energy. But that's not actually what it goes back to. It goes back to the fact that when you're doing rotation, the problem can be looked at almost exclusively as rotation if you set it up as that. And the particular sticking point, the one thing that you really have to pay attention to, was whether or not you were using the moment of inertia of the rolling object, where the axis of rotation goes through the center of mass, or was the axis of rotation some other point that wasn't through the center of mass, and that's the moment of inertia you used. So hopefully you'll see in this example, I'm going to demonstrate for you how you actually set that up so that hopefully it's perfectly clear and it doesn't cause you any problems. So all I wanted to do right now is just pull up our notes that we had taken on the proof of our parallel axis theorem and point out that the proof is really all about rotational kinetic energy. And when we are breaking this apart, this is the rotational kinetic energy for the object as a whole. And then on the right side, we're dealing with rotational kinetic energy. This K rotational here deals exclusively whenever the moment of when the axis of rotation is going through the center of mass for the object. And this is whenever the axis of rotation is not through the center of mass of the object. And so if the axis of rotation is not going through the center of mass, and we are using the moment of inertia, which is not through the center of mass, then we have included K translational within this new moment of inertia. It takes into account that we have translational kinetic energy. That's the best way I can explain it to you. We see that as we go all the way through to the end here, that this I, which was based on kinetic energy, is going to be equal to this I, or the kinetic energy of rotation, and this I, which is, not I, but this kinetic energy term, which is based on just the motion of the center of mass. So that might sound a little bit confusing, but let's go ahead and get started with our actual example, and I think it's going to make a whole lot more sense once you see that. Okay, so I've left this statement up here that says, if the axis of rotation is in motion at the instant of the analysis, then you must include K translational. If the axis of rotation is stationary, there is no K translational, and that's because the moment of inertia, the new moment of inertia that you're going to use, will have already accounted for the additional energy requirements of a center of mass being in motion. So in this first part, we're going to place the axis of rotation in the traditional way, which we would place through the center of mass. So right here is going to be the axis of rotation for this first part of the problem. And we're just going to do a simple one. We want to know where is this, or how fast is this ball going to be moving when it reaches the bottom of the hill. So this is a ball. Might as well write that down so that we know. Don't forget that this is a ball, not a disc. And we're going to say that y is equal to 0 at the bottom of the ramp. That would be also a very traditional place for it. And we're looking here at the height of the ramp. Okay, so anytime we do a conservation problem, we start with delta E is equal to 0. And so in this case, we're going to write out delta K plus delta UG plus delta K rotational is equal to 0. And so we have K final minus K initial plus UG final minus UG initial plus K rotational final minus K rotational initial is equal to 0. All right, so at the top of the ramp, there's no motion at all, and so we can eliminate all the initial kinetic energy terms. So that one goes to 0, and this one's going to go to 0. And at the bottom of the ramp, there's no more gravitational potential energy, so UG final is going to go to 0. And now we can simplify and rewrite it, get rid of all these excess terms, and we're going to have K translational final plus K rotational final is equal to mgy initial. Now at this point, I'm just going to pause for a moment and say that this particular statement right now is basically telling us that all of the gravitational potential energy is going to be shared between these two forms of kinetic energy, translation and rotation. And therefore, we would expect the object to be moving slower, because prior to rotation, all of our kinetic energy was translation. And so the more energy you have to translate, the faster you're going, right? But now that we have to share this one, pot of energy, if you will, now that we have to share it, K translational is going to have to be less than what it was before. Okay, so let's go ahead and expand this out, finish it up very quickly, the traditional approach, and we have 1/2 mv squared plus 1/2 I omega squared is equal to mgy initial, and I is just that for a sphere which is rotating around its center of mass. And so this is going to become, I'm going to multiply everything through by 2 to get rid of my 1/2, and so we'll get mv squared plus 2/5 mr squared omega squared is equal to 2 mgy initial. And now we can cancel out the m's rather conveniently. And now all we have to do is get this in terms of velocity. So omega squared, that's going to have to become, using the bridge equations, v is equal to omega r. So omega is equal to v over r. And this is going to become v squared over r squared. So we have v squared plus 2/5 r squared v squared over r squared is equal to 2g y initial. Almost done. We can cancel out these r squareds here. That one was squared. And so what we end up with is v squared, or 5/5 v squared, plus 2/5 v squared, or 7/5 v squared. And when we bring that to the other side, we're going to multiply it by 2. We end up with 10/7 gy initial is equal to v squared. All right, so that's the answer that we get using the traditional approach. Now let's take a look at the non-traditional approach. In the non-traditional approach, we're going to move our axis of rotation to this point right here. Now, when this ball is rolling down the ramp, it's in the middle of rolling down the ramp. When I look at the axis of rotation through the center of mass, I know that the center of mass is actually in motion, and therefore, according to this rule that I've written out for you, I'm going to use translational kinetic energy because the axis of rotation itself is in motion. Now, if we use this point of contact, then we know when you're rolling without slipping that at the instant the axis of rotation would be in contact with that surface, the velocity is equal to 0. And if the velocity is equal to 0, then we're not going to include translational kinetic energy. So let's take a look at the non-traditional approach now. Okay, so non-traditionally what we have is delta E is equal to 0. So we're going to write delta K plus delta K rotational plus delta UG is equal to 0. And now we're just going to acknowledge the rule that says that the axis of rotation is at rest, and so I do not need K translational, so that whole term goes to 0. So I'm going to have K final minus K initial plus UG final minus UG initial. And just remember that this is K rotational. All right, that's going to be rotational. I'm just not putting the extra subscript in there. So we know that we're going to lose K initial to 0 because there's no kinetic energy when it starts at rest. And when it reaches the bottom of the ramp, UG final is going to be 0. Okay, and so now let's expand it out. So what we end up with is 1/2 I omega squared is equal to mg y initial. And you're looking at that and going, wow, that is just a much, much easier way of solving the problem. And I would agree that it generally is a much easier way of solving the problem. But we still have, I'll call them sticking points, because we have to remember to do certain things. In particular, what do we do with moment of inertia? That's the thing we have to be careful with. And so when it comes to the moment of inertia, remember that we're no longer rotating around the center of mass. And so now we have to use the parallel axis theorem, which says ICM plus MD squared. All right. Now remember that this basically is accounting for translational kinetic energy, this particular term of the parallel axis theorem. And that's so easy to miss. I missed it for years personally. So that's why I'm emphasizing this, because as a new student of physics, I mean, even though this is probably your second year, you're still basically a new student of physics. And that's an easy thing to miss. All right, so ICM is 2/5 mr squared plus m. And now when we look at the ball that's rolling down the ramp, the axis of rotation starts here. The ball has a radius of r. And so whenever you move the axis of rotation down in this direction, right? When you put the axis of rotation there, you're saying that the d value is going to be just the radius of the ball. So we have 2/5 mr squared plus 5/5 mr squared, which gives us 7/5 mr squared. So we'll substitute that back, and we get 1/2 times 7/5 mr squared. Omega squared, we can rewrite omega. Remember that we're trying to find velocity here, so omega is going to be equal to v over r. So omega squared is v squared over r squared. So we have v squared over r squared is equal to mgy initial. So let's cancel out those terms that cancel. R squareds cancel. Mass cancels. And now we can rewrite this, simplify it down. We have 7/10 v squared is equal to g y initial. So v squared is equal to 10/7 gy initial, which is exactly what we got using the traditional approach. See right there, we have 10/7 gy initial. 10/7 gy initial. Okay, so that's it for this video. Just remember that if you have your axis of rotation as stationary and you write the moment of inertia for that axis, then you will not use translational kinetic energy.